So first of all, I would like to thank the organizer for organizing this workshop. So today I will present my research on exact statistical inference for the Wasserstein distance by selective inference. So this is a joint work with my supervisor Ichiro Takashi. So this is just a brief introduction about myself. So I'm Nguyen Le Duy. So currently I'm a PhD student at Nagoya Institute of Technology. So I'm also a junior research associate at RIKEN. So my research interests including statistical machine learning, hypothesis testing, and selective inference. So this is the outline of my presentation. So it includes 3 parts. So in part 1, so I will point out the reliability issues problem in machine learning with an example on the Wasserstein distance. Then in part 2, I will present a selective inference framework, so which is recognized as a new promising approach for quantifying the uncertainty or statistically guarantee the reliability of the data-driven machine learning result. And finally, in part 3, I will present an approach to quantify the uncertainty of the Wasserstein distance by using the concept of the conditional selective inference. So now let's start with part 1, uncertainty in machine learning. So nowadays, machine learning algorithms have been developed as a powerful tool for data analysis tasks, and is used in various numerous domains. Unfortunately, the results of the obtained from machine learning algorithm might be too overfit to the data, and we might obtain a lot of false discovery. So using these false results are harmful for high-stake decision-making in a lot of practical applications. So for example, medical diagnosis or automatic driving. So this is an example in the case of the Wasserstein distance. So the Wasserstein distance is a metric used to compare the probability distribution. So the Wasserstein distance measures the cost to couple one distribution with another distribution. So this distance arises from the notion of optimal transport. So this figure, so an example is shown in this figure. So given the data, the source targets in blue and the targets, the source instance in blue and the target instance in red. So our goal is to compute the Wasserstein distance between the source instance and the target instance. So first we input the data to a linear program, and then we obtain the transportation map. So finally, then based on the transportation map, so we obtain the optimal coupling between the source instance and the target instance. So here the orange line is the optimal coupling between between the source instance and target instance. And finally, based on this optimal coupling, we can obtain the Wasserstein distance. So the Wasserstein distance has attracted a lot of attention and has been used in various machine learning tasks. So the utilization of the Wasserstein distance benefits to several applications. For example, it can be used as a loss function in a supervised learning, generative modeling, or computer vision. But unfortunately, when the Wasserstein distance is uncertain when it is calculated under the noisy environment. So more specifically, when the Wasserstein distance is calculated from the noisy data, the uncertainty in the optimal coupling leads to the uncertainty of the Wasserstein distance. So this is because the Wasserstein distance is calculated based on the optimal coupling. Therefore, it is highly necessary to quantify the statistical reliability of the Wasserstein distance when it is used for the practical application or used to make the decision in high-stake decision-making problem. So one way to quantify the statistical reliability is to provide the confidence interval for the Wasserstein distance. So reliability of machine learning has been discussed for various aspects. So for example, that is statistical inference, including hypothesis testing, confidence interval, facility, fairness, and robustness. In statistical inference, there are mainly 2 approaches, frequentist approach and Bayesian approach. And in frequentist approach, there are also mainly 2 types of conducting the inference, that is non-asymptotic inference and asymptotic inference. And in these studies, I will mainly focus on the frequentist-based exact statistical inference. So our goal is to provide the non-asymptotic exact confidence interval for the Wasserstein distance. So the confidence interval is well known as a fundamental approach for reliability quantification in science. So a confidence interval is a range of the value that we are fairly sure that the true value of the unknown parameter of interest lying. So this is the general recipes for constructing a confidence interval. So first, we need to identify the unknown parameter of interest. And then at the second step, we need to construct a test statistic, which is a function of the data. The test statistic here can be seen as the observation of the unknown parameter. And finally, the confidence interval of the unknown parameter is computed based on the test statistic that we identify at the second step. Here's the main challenge is how to compute the valid confidence interval for the data machine learning result. So the question is why it is challenging? Why is it difficult? So in traditional method, the traditional confidence interval computation is simple. This is because of the parameter of interest is predetermined before we collecting the data. So therefore, no data selection bias exists. But in contrast, in machine learning, so we first collecting the data and then applying the machine learning algorithm on the data to observe the parameter of interest. So in other words, the parameter of interest is data-driven and defined after collecting the data. Therefore, data selection bias exists, and we must and proper bias correction is required to compute a valid confidence interval for the data machine learning result. So there are some existing methods for correcting the selection bias in data-driven machine learning. The first one can be multiple testing, multiple comparison, for example, morphology correction. But unfortunately, in this scenario, multiplicity is unrealistic because a huge number of possible hypotheses can be generated by the machine learning algorithm. For example, in the case of the Wasserstein distance, if we want to use multiple testing comparison to correct the selection bias in the Wasserstein distance, we need to enumerate all possible coupling between the source instance and the target instance, so which is unrealistic and unfeasible because we cannot generate all possible coupling. So another approach is the data splitting. But however, in the data splitting, the information in the data is wasted. So we lose the power. We lose the power both in selecting and evaluating the data-driven hypothesis. Besides, the data splitting is also not applicable for several tasks such as unsupervised learning or representation learning. So this is the summary of part one. So although the literature related to machine learning algorithm is huge, so less attention has been paid to statistical reliability of the machine learning result. Confidence interval is well known as a fundamental approach for reliability evaluation. However, there is no general and practical framework that can properly compute the confidence interval for the data machine learning result. So in the next part, I will present a new promising approach to compute the confidence interval for the data-driven machine learning named Conditional Selective Inference. So now let's move to the part two, Conditional Selective Inference. So selective inference has been recognized as a new promising approach to access the statistical reliability of the data-driven machine learning. The basic idea of conditional selection is that we will make the inference conditional on the event that the parameter of interest is identified by machine learning algorithm. Then by doing the conditional inference, the valid confidence interval can be computed. So this is the picture. So we first collecting the data, then the applying machine learning algorithm on the data to identify to obtain the parameter of interest. And after that, we construct the test statistic, and finally, the confidence interval is computed by using conditional selection inference. So this is the concept of the selection inference by schematic illustration. So given the observed data, this is observed, we first applying machine learning algorithm on the observed data and obtaining the hypothesis A. So in the case of the Wasserstein distance, hypothesis A can be corresponding to the optimal coupling on the observed data. And then we will try to search at the second step. We will want to search the region where the same hypothesis A is obtained. So for example, in this figure, when we apply machine learning algorithm on the purple data point, we obtain the same hypothesis A as the observed data we observe. And therefore, the reason that we want to identify is the reason that containing all these purple points. And finally, at the first and final step, the confidence interval is computed by considering the conditional sampling distribution of the test statistic, conditioning on the conditional data space that we identify at the second step. So by doing the conditional inference, we can remove the selection bias in the data-driven machine learning, and we can conduct exact statistical inference for the data-driven machine learning result. So up to now, I've already presented the main concept of selective inference. So here is a summary of part 2. So selective inference has been actively studied as a promising approach for statistically quantifying the reliability of data-driven machine learning results. A valid confidence interval can be computed by conditioning on the event that the parameter of interest is selected. So in other words, by conditioning on the selection event, the exact sampling distribution of the parameter of the interest can be analytically identified. So this is the general framework for quantifying the reliability of the machine learning result. So first, we initially collect the data. Then at the first step, we apply machine learning algorithm on the data to obtain the parameter of interest. Next, constructing the test statistic, and finally, the valid confidence interval is computed by using the concept of conditional selective inference. So now I will move to the part 3 of the presentations. So in part 3, I will present an exact statistical inference method for the Wasserstein distance by using the concept of the conditional selective inference. So here, consider the two observed vector X observed and Y observed sample from this model. So here, capital X is the random variable, mu of X is the true vector, and epsilon X is the Gaussian noise. Similarly applied to the Y, and X observed can be seen as the blue data points, and the Y observed is considered as the red data point. And then after observing the data, we apply a linear program on this data and obtain in the optimal coupling M observed, script M observed. So this is the optimal coupling. So the optimal is represented at the orange line. And after obtain the optimal coupling, we can easily compute the Wasserstein distance. And then our goal is to provide the confidence interval for the Wasserstein distance that we compute at the previous slide. So here, the confidence interval is considered to be valid if the probability that it can cover the true value of the Wasserstein distance is equal to 1 minus alpha. So here, 1 minus alpha is the confidence level and given by the user. Unfortunately, constructing the valid confidence interval for the Wasserstein distance is challenging because the optimal coupling is selected based on the data. So in traditional method, we need to fix the optimal coupling in advance. But in the case of data-driven machine learning, the optimal coupling is decided based on the data. Therefore, to compute the valid confidence interval for the Wasserstein distance, we need to remove the data selection bias. So in other words, we need to remove the selection bias of selecting the observed optimal coupling. So finally, therefore, we introduce an approach to remove the data selection bias by in the case of Wasserstein distance based on the concept of the conditional selective inference. So this is the proposed idea. So we propose an approach to avoid the data selection bias by considering the distribution of the Wasserstein distance conditional on the optimal coupling. So here, more specific here, X and Y is any random vector, and script M of X and Y denote the optimal coupling between any random vector X and Y. And here, by considering the sampling distribution of the Wasserstein distance conditional on the space where we obtain the same optimal coupling as the observed data, then we can successfully remove the event of selecting the observed data. In other words, we can, by doing this conditioning, we can remove the data selection bias. And finally, the conditional sampling distribution of the Wasserstein is a truncated normal distribution, which can be analytically characterized and used to obtain the valid confidence interval. So this is the schematic illustration of the proposed methods. So first, we observe the observed data X observed and Y observed. Then we apply a linear program on the observed data and obtain the optimal coupling. After that, at the second step, we need to search for the region where the same optimal coupling is obtained. Here, when we obtain for the purple point, we obtain the same optimal coupling as the observed data. And finally, by considering the sampling distribution of the Wasserstein conditional on this conditional data space at the second step, we can successfully identify the exact sampling distribution of the Wasserstein distance. So, which is subsequently used to compute the confidence interval. This is all for the proposed method. So this is slide show the experimental results on the synthetic data. So here we evaluate the performance of the proposed methods in terms of coverage guarantee, confidence interval length, and the computational cost. Yeah, in the left figure, the orange line is the naive method, so where we does not correct the data selection bias, and the blue line is the proposed confidence interval. So the naive method cannot properly guarantee the coverage property because obviously it's invalid because it does not take into account the data selection bias. But in the case of method, by doing conditioning, we can avoid the selection bias. Therefore, the proposed selected confidence interval can successfully guarantee the coverage property. The result in the middle plot indicates that the larger the true distance between the source instant and the target instant, the shorter interval that we obtain. So here delta represents the true difference between the source instant and the target instant. And finally, the results in the right plot shows that the proposed method also has reasonable computational cost. And this slide shows the experimental result on real data. Here we consider the breast cancer dataset and lung cancer datasets, and the setting is as follows. Given a dataset with two classes, class 1 and class 2, we either choose 5 instances from the class 1 and 5 instances from class 2, or selecting both source instant and target instant from either class 1 and class 2, then compute the confidence interval. And we repeat this process up to 120 times. So this is the result on breast cancer dataset and lung cancer dataset. So this result indicates that the confidence interval of the Wasserstein distance in the case of different class is shorter than the one computed in the case of the same class. So this is because when the data are different from the different class, so the Wasserstein distance tends to be larger than the one computed in the case of the data are from the same class. So this is the end of the work of the Wasserstein as a conditional selection inference for the Wasserstein distance. So here are the summary of my presentation. So reliable machine learning is one of the most important issues in the machine learning community. Traditional method cannot be used to evaluate the reliability of the data-driven machine learning result. Conditional selection inference is a promising approach for statistically quantifying the reliability of the data-driven machine learning. So in this work, in this study, we propose an exact non-asymptotic inference method for the Wasserstein distance based on the concept of conditional selection inference. And this is the first method that can provide a valid confidence interval for the Wasserstein distance with finite sample coverage guarantee. So finally, the take-home message is that to quantify the reliability of data-driven machine learning, we need to correct the data selection bias. And the main concept of selecting inference is that by conditioning on the data selection event, we can avoid the selection bias, and it's applicable to the case of Wasserstein distance. in the case of Wasserstein system, the optimal coupling is data driven. Then to remove the data selection bias, we can conditioning on the optimal coupling, and then by conditioning on the optimal coupling, we can derive the exact sampling distribution of the test of the Wasserstein distance. So which then we can compute the confidence interval for the Wasserstein distance. Yeah, so that's all for my questions. Thank you so much for listening. So if you have any questions, so I'm very happy to answer and discuss.
Thank you very much.
Yeah.
So then, may I first ask a question?
Yeah, sure.
So I think selective inference is a quite interesting concept.
Yeah.
But the first paper has been published already more than 5 years ago.
Yeah.
So I think the methodology has been already improved a lot. But how is the practical applications? Like, do communities of physics, medicine, so do they accept selective inference in their community?
At the moment, I mean, I think are changing, and I think they are changing, and they are trying to accept that, because that
like when they publish papers, do they use p-values obtained from selective inference rather than t-test?
I think yes, because that if they use machine learning method, then they need to apply. They need to because when they use machine learning, they will need to using some statistical inference method for the machine learning for the data driven area. So one possibly, and they use the asymptotic method, and now selective inference method is another method that is not asymptotic, and I think that they can use selective inference as the
I understand. So in principle, using selective inference is more appropriate, but it's a kind of rule of the game, right? Do they change their rule?
I would say
and require authors to use selective inference to validate their result.
I would say that not yet popular. So so we need to show them the importance, and I hope that they are now changing.
Okay, thank you very much. So then, any other question? If there's a question from the EPFL side, can somebody speak? But how many people are there in EPFL?
So maybe we can show the room right now. This part people are not sitting because it's within the visual zone. So trust me, there are people. I think maybe more than 30 current.
Oh, that's great.
Yeah, so they are hidden and crouching. So yeah, there are more people. The room is pretty big. Yeah. So questions, any questions from here? I think we should have some sort of so we will discuss this. So maybe initial questions from the side that gives the presentation, then we can have the remaining questions from the other side. There is one question from Guillaume Obozinski.
Hello, thank you for your very interesting talk. I have a question which is a bit of a naive question. So, I mean, the methodology of conditional selective inference is quite elegant, but at the same time, so this is all relying on conditioning on the set that you construct.
Yes.
Right. So in this, if let's say you were trying to use another method, like for example the bootstrap, to obtain a confidence interval for the same quantity, like through resampling, you would probably have find different matchings between the different data point sets, right? So, like, could you comment on essentially how this methodology affects the intervals that thing compared to other approaches?
Okay. So thank you for your question. So so in my understanding, so for example, if you use bootstrap or something, so you cannot so first the main advantage of by using the conditioning in selection inference is that we can obtain the exact sampling, not approximation, but exact sampling distribution of the exact sampling of the test statistic. So which means that we can derive the sampling distribution in finite sample size. Or yeah, but if you use another method, for example, non-asymptotic approach, so you cannot have maybe when you have few data, you cannot successfully derive the sampling distribution of the test statistic of the quantity. So the main difference is that by doing conditioning on the selection, we can derive the exact sampling distribution of the test statistics. So which means we can make the exact inference rather than non-asymptotic inference. So that is the main advantage of the conditional selection inference. So that's my answer your question.